Integration by parts can be a drag if you have to do it multiple times. So let's look at a method for doing it multiple times that's a little bit less of a drag. So suppose we write the integral of u dv equals uv minus the integral v du, and we find that we can't do this integral either, so we have to do integration by parts again. So let's organize this integral into something like the integral of w dz, where we can differentiate w and we can integrate z, we can integrate dz, and then this is wz minus the integral of z dw. Well, since the integral of v du came up with a minus sign here, then this second minus sign really becomes a plus. These signs are really minus and plus, so we have to be careful about the sign change. And then if we're integrating something like p of x e to the minus x, then every time we integrate this exponential function, we've got another minus sign coming into the picture, which gives us another opportunity to get signs wrong. So with all these minus signs, it's a little bit hard to keep our work neat and get the signs correctly. So I claim that if u is a polynomial of degree k, so its k plus first derivative is 0, then we want to integrate u dv, then this just turns out to be uv minus first derivative times first integral of v plus second derivative of u times, I'll write double integral of v, so integral of the integral, minus third derivative of u times the third integral of v, etc., up until we get to the last derivative of u that's not 0. So that'll be the kth one. And it's going to come up with a sign which depends on whether k is odd or even. So minus 1 to the kth derivative of u, and let me write integral sign with a k for the kth integral of v. Plus c, because I'm writing this as an indefinite integral. Alright, so to prove that this is true, we could just take the derivative of this expression and see that we get u dv. So differentiating, we have, let's see, start with this. We have derivative of the first times the second plus derivative of the second times the first. I'm going to write all the u's first and the v's second. So plus derivative of the second times the first. Then we have minus derivative of the first times the second plus derivative of the second times the first, then plus derivative of the first times the second plus derivative of the second times the first etc. Let's skip to the k minus first derivative here. So we'll have a negative 1 to the k minus 1. I didn't write down this term, but it's negative 1 to the k minus 1, k minus first derivative of u, k minus first integral of v. So then we get derivative of the first times the second plus derivative of the second. So derivative of k minus 1 integrals is, I guess, k minus 2 integrals only times the first. And then finally the last term, minus 1 to the kth. Derivative of the first. Well, derivative of the kth derivative of u is going to be 0. Plus derivative of the second. So k minus 1 integrals only of v times the first. Alright, so that's the end. Then we'll see that a bunch of these things appear twice, once with a positive sign and once with a negative sign. So u prime v appears here with a positive sign, there with a negative sign. U double prime integral of v appears here with a minus sign and there with a plus sign, etc. So we're going to get cancellation, 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 all the way down to the last cancellation is kth derivative of u times k minus first integral of v. Whatever these signs are, they're opposite. So after cancellation, we are left with what's left. uv prime, also known as u dv, which is what we want. Alright, so let's do an example of this. Now in practice, I think I wouldn't write it out exactly the way I did in the claim. So if we have we can make a u column and a v column. And then keep taking derivatives of u and keep taking integrals of v. And then we connect on this diagonal and we write plus, minus, and sum the products of the connected factors. With the signs that we just put on the line segments. So for example, let's say we wanted to integrate 1/4 the integral from 0 to infinity of x plus x squared over e to the x dx. So this divided by e to the x is really times e to the minus x. which means that when we take multiple derivatives of x plus x squared until it gets down to 0, we're integrating e to the minus x and picking up a negative sign on top of the negative signs that happen with the regular integration by parts. So we can write x plus x squared, its derivative 1 plus 2x, derivative of that 2, derivative of that is 0. So we stop here. And this is really times e to the negative x. X plus x squared times e to the negative x. So write e to the negative x here. Integral of that is negative e to the negative x. Integral of that is e to the negative x. Integral of that is negative e to the negative x. Connect, connect, connect. Write plus, minus, plus. And apparently the integral of x plus x squared e to the negative x is x plus x squared minus x plus x squared e to the minus x minus 1 plus 2x e to the negative x minus 2 e to the negative x, which is, we can factor out e to the negative x, and we've got, well, let's see, we have minus x squared minus 1 minus 2x minus 2. So in total, we have minus x squared minus 3x minus 3 over e to the x plus c. All right, now we want to multiply this by 1/4 and take the integral from 0 to infinity. So this is 1/4 the limit as b goes to infinity of, let me write minus 1/4 and get rid of these minus signs. X squared plus 3x plus 3 over e to the x as x goes from 0 to b. Alright, we plug in b and let b go to infinity. The denominator is going to go to infinity much faster than the numerator. So that'll just be 0. And then we plug in 0 and we get 0 plus 0 plus 3 over e to the 0th. Which is negative 1/4 times minus 3, which is 3/4. So there we have it, and I think this allowed us to take care of the signs sort of neatly and maybe protect us from making sign errors. The end.